Every year, nearly 10 million tons of citrus fruits, mostly oranges, leave orchards around the world, bound for distant ports, markets, and supermarket shelves. To the untrained eye, this may seem like just another export statistic, but behind that number is an industrial choreography so complex and delicate, it rivals any factory assembly line. Oranges, unlike steel or grains, are fragile biological spheres. Each one is composed of about 85% water, enclosed in a soft membrane of cells that rupture under pressure. Now imagine stacking them, pallet after pallet, into 40-foot steel containers, moving them across roads, ports, and oceans, without a single rupture, triggering microbial decay. That's not just logistics, it's physics, engineering, and biological preservation, synchronized to the second. At this scale, gravity becomes a silent adversary. When tons of fruit are stacked on top of each other, the pressure isn't uniform, it concentrates. Left unaddressed, this vertical stress can crush the fruit at the base, triggering chain reactions of bursting and rot. That's where an unlikely source of inspiration enters: the mining industry. Mechanical engineers who once studied the flow of crushed ore inside vertical silos lent their expertise to citrus logistics. They understood that pressure needs to be diffused, redirected, absorbed. Crates were redesigned to behave like engineered silos, distributing weight through load paths that prevent collapse. It's not just about stacking, it's about understanding flow dynamics inside a crate, the way one might analyze airflow through a jet engine. But structural design is only one layer of this operation. Timing is another. From the moment a citrus is harvested, the countdown begins. Every hour that passes accelerates biochemical changes: citric acid degradation, enzymatic browning, volatile loss. That's why the entire post-harvest chain, picking, washing, cooling, packing, loading, must happen in less than 72 hours, not by improvisation, but by design. Dynamic route optimization algorithms manage everything from the harvester's path in the field to the truck's arrival at the port. If a truck is delayed by just 4 hours, it can mean a 2% loss in acid integrity. At global scale, that's the taste of millions of oranges quietly slipping away. To move that volume with such care, citrus exporters have looked back in time. In the 1950s, coal exporters faced a different but related challenge: how to move brittle material onto ships without fragmentation. The solution was synchronized conveyor belts that moved with a rhythm, not too fast to crack the coal, not too slow to bottleneck the port. Today, a similar principle is applied to citrus terminals. Conveyors are calibrated not just for speed, but for kinetic softness. Loaders use soft drop systems. Belts are timed to avoid microbursts, those sudden drops that can create pressure spikes and bruise the fruit. What looks like a simple packing line is, in reality, a choreography of belts, buffers, and human oversight. This is the silent orchestra of citrus exports. It's not about moving fruit. It's about harmonizing materials, time, and temperature in a sequence so tight, a misstep anywhere could echo across thousands of kilometers. Sensors read humidity inside crates. GPS systems guide cold trucks with second-by-second precision. Biological behavior meets mechanical intelligence in a chain that doesn't rest, doesn't blink, and can't afford to fail. In this ballet of machines and molecules, every crate, every orange, and every second counts. What emerges is more than a trade flow. It's a lesson in agro-industrial orchestration, a system where harvesters, loaders, algorithms, and packing belts perform in tune, each responding to the limits of biology, the demands of global commerce, and the discipline of engineering. Welcome to the invisible architecture behind your morning orange juice. Once inside the container, the fruit seems safe, stacked, sealed, cooled. But the risk hasn't passed. It has only changed form. What threatens citrus in this stage of the journey is no longer physical pressure, but temperature differentials that develop in silence. Most temperature sensors in shipping containers are placed near the walls or at the air outlets. But the true danger lies at the center, at the thermal heart of the load, where crates press against each other and airflow becomes sluggish. While external readings may show a stable 0 degrees Celsius, inner palates can silently climb to +4 degrees. That's enough to activate dormant fungal spores living in microcracks on the fruit's surface, triggering internal rot that only reveals itself days later. Citrus fruit, even after harvest, continues to live. It respires. It exchanges gases. It generates heat. As ethylene accumulates inside a poorly ventilated space, it accelerates ripening, fermentation, and decay. A single 20-ton shipment, if left without proper post-harvest cooling, can begin self-fermenting within 36 hours. In this microbial race, time isn't just money, it's aroma, texture, and taste lost in a thermal fog. That's why the first stage of shipping isn't transport, it's respiration control. And that begins with air, how it moves, where it reaches, and how it interacts with the cargo's design. Here's where engineering still meets its blind spots. Reefer containers, designed for general cold cargo, often fail when it comes to citrus specifics. Studies have shown that up to 70% of air vents in these containers are misaligned with the crate perforation patterns used by citrus exporters. That means cooled air doesn't flow into the fruit stacks. It dances around them. The result is thermal stratification, colder air around the edges, warm pockets in the core. In a biological cargo, such a small miscalculation turns into a system-wide vulnerability. It's like cooling the outside of a loaf of bread while the inside continues to bake. And the consequences are tangible. One citrus exporter in southern Spain loaded 14,000 boxes of Valencia oranges bound for West Africa. The voyage to Senegal lasted just under 9 days. But poor ventilation planning, combined with an unbalanced stacking pattern, created dead zones with zero airflow. By the time the ship docked, mold had formed inside nearly every central pallet. The entire shipment was discarded, a loss of over $800,000, not because of a storm, delay, or pest, but because of stagnant air and a few extra degrees. This is where new technology emerges, not as luxury, but as necessity. Today, smart crates embedded with microsensors can detect carbon dioxide buildup, humidity variation, and airflow blockages in real time. When something starts to go wrong mid-journey, the data triggers route changes, adjusts cooling protocols, or even activates airflow rebalancing systems. These are not gadgets. They are tools for survival, mechanical extensions of biological insight. When citrus is packed not just with care, but with data, it becomes more than fruit. It becomes a monitored entity, one that travels the world under watchful eyes, invisible to most. Before we continue, stop and think about this. If a difference of just 4 degrees can destroy an entire shipment of oranges, imagine the level of precision required to make global agriculture actually work. That same attention to detail inspired something we've prepared for you. Check the pinned comment. It's something made with the same focus on quality, and it might surprise you. Citrus doesn't wait. The moment it's separated from the tree, a silent transformation begins. It may look unchanged on the outside, but inside, chemical signals activate. Enzymatic reactions are triggered by the sudden drop in water flow, initiating the breakdown of aroma compounds and increasing the concentration of bitterness. Within 240 minutes, if the fruit hasn't been cooled below 10 degrees, the damage is irreversible. That window, 4 hours, is the thermal point of no return. And across orchards that span hundreds of hectares, meeting this deadline becomes an exercise in logistical precision. Yet precision is often disrupted by the chaos of scale. In large cooperatives, where thousands of crates are harvested simultaneously, even a small failure in scheduling can create heat traps. Crates left under the sun accumulate surface temperatures of 30 to 32 degrees Celsius. At that point, the wax layer that naturally protects the peel begins to deteriorate. The oils oxidize. The skin becomes vulnerable, not just to physical handling, but to microbial invasion during washing. What follows isn't visible damage, it's internal decline. A citrus fruit that looks perfect may already be losing shelf life minute by minute because it stood too long in the wrong place. To address this vulnerability, a new concept has emerged: the inline hydro-cooling corridor. It's not a machine, but a system. Mobile cooling tunnels are now being deployed between the orchard and the packing station. As soon as the fruit is loaded, it passes through these corridors where chilled water is sprayed and circulated with controlled pressure. In just 15 minutes, the fruit's core temperature drops by 12 degrees. The result isn't just a cooler fruit, it's a stabilized one. Peel waxes remain intact, respiration slows, microbial resistance is preserved. It's a quiet technological triumph hidden behind a fine mist and the sound of spinning fans. The engineering approaches to this vary across countries. In Brazil, the system tends to be static. Fruits are collected and cooled in batch silos. In Spain, the model is dynamic. Crates move in continuous flow, guided by laser-triggered thermal sensors that adjust the speed and pressure of cooling based on the fruit's initial temperature. This means no two crates are treated the same. Each one receives the cooling it needs, not the average cooling assumed by older systems. The difference is measurable. Yield losses in Brazilian systems can be 3 to 6% higher, simply due to the limitations of uniform treatment in a variable climate. Now, new logistics platforms are introducing climate-responsive cooling thresholds. They integrate field temperature data, weather forecasts, and harvest times to automatically adjust the rate of ventilation, cooling, and transfer. What used to rely on experience and human intuition, feeling the heat of the crates, estimating urgency, has been replaced by systems that see what we cannot. The fruit is still picked by hand in many places, but from that moment on, every decision is informed by invisible algorithms. It's not just cooling, it's climate synchronization, executed in motion to protect taste before it ever has a chance to fade. There is a misconception that logistics is simply about movement, about getting something from one place to another. But in the citrus industry, logistics does more than transport. It shapes taste. Each decision, from the speed of the conveyor belt to the cooling threshold in a container, directly alters the fruit's biochemical profile. Sugars mature, acids stabilize, and aromatic compounds preserve or dissipate depending on how precisely each stage is handled. Logistics becomes a flavor engineer, and what arrives in the hands of a consumer is not just a fruit. It is the result of thousands of orchestrated choices made in fields, in packing houses, and inside software systems. Yet this orchestration remains vulnerable to human oversight. Chain of custody decisions, like when to pick, how long to wait before cooling, or which shipment to load first, require not only knowledge, but foresight. A slight misjudgment in the ripeness window can mean exporting citrus that is too green to ripen properly in transit, or too ripe to survive the journey. In both cases, the result is waste, not just of product, but of water, energy, labor, and time invested over months. A single poor decision, even with the best technology in place, can unravel everything. To understand this system, imagine the gearbox of a high-performance agricultural machine. Every gear, bearing, and shaft must move in perfect synchrony, transferring torque without loss, ensuring maximum efficiency. In citrus logistics, the mechanical parts are the harvesters, loaders, and crate systems. The digital layer, telemetry platforms, tracking sensors, algorithmic route planners, acts as the control unit, and the fruit's biological responses are the output. If one cog slips, if a harvester runs late, or a sensor gives false data, the whole system slows and the output falters. This is not just coordination, it is torque equilibrium applied to perishables. In Japan, this logic has been elevated to near perfection. Premium citrus destined for luxury markets is handled by automated logistics chains, where robotic sorters detect fruit density, measure peel tension, and respond in real time to ensure only the most stable specimens proceed to export. Conveyor gates are triggered by AI-driven decisions, ensuring that fruit is not only categorized for quality, but directed into optimized routes based on its predicted shelf life. With this level of control, exporters have achieved a 98% accuracy rate in post-export shelf life, maintaining flavor integrity for up to 30 days. not through guesswork, but through a tightly integrated system of data, mechanics, and biology. What this reveals is profound. Citrus isn't simply transported, it is mechanically curated. From the moment it is picked, each fruit enters a machine-like sequence designed to protect what cannot be rebuilt: flavor, freshness, and resilience. The logistics chain becomes a kind of silent laboratory where taste is engineered in motion. Every valve, crate, and temperature threshold is a decision point. Every sensor is a lookout post guarding against entropy. In this vast, often invisible architecture, technology doesn't just move food. It preserves the essence of life inside each fruit. And that, quietly, is how engineering helps feed the world. In a world where taste depends on timing and precision, even the smallest decisions shape the final experience. And speaking of small decisions that make a difference, if you've made it this far, don't miss the pinned comment below. It's there for a reason.